I'm Alexandra Brintrup. My pronouns are she and her. I'm white and have curly brown hair. I'm wearing a gray t-shirt. My main research interests are AI, particularly agents and heuristic algorithms in supply chains and logistics. So I'll be giving today a short talk on our feasibility study, AgentChat, which has been funded by the Connected Everything Network. Our team members, whom you will meet shortly in the panel session, include Limin Zhu, Stephen Mack, and Stefan Schöpf from the University of Cambridge, and Michael Ostermo from the Value Chain Lab, and Maria Minarikova from Fetch AI. So the primary motivation for our project has been sustainability. As many of you probably are aware, the UK is committed to reducing carbon emissions by 2050, and we need to find ways to embrace this target and incorporate it in our daily lives. So logistics is one such carbon generating activity that impacts all of us. Everything you have in your home has in some way been delivered from somewhere to be with you. So most of that stuff is carried with what we call heavy goods vehicles, which account for 5% of the UK's total greenhouse gas emissions. Unfortunately, freight capacity in the UK is significantly underutilized, which leads to higher costs, environmental damage, and congestion. Only 63% of journeys carry useful load, and the average vehicle utilization is under 60% by weight or volume. So what we wanted to investigate in this particular feasibility study is collaboration in logistics, which simply involves the sharing of truck capacity between one or more sending parties to receiving destinations. So both academic and industrial research estimated that collaboration can improve vehicle fill and remove unproductive journeys, with a potential of about 20% cost savings for the different parties involved. But this does not happen today because of what we call in academia an information asymmetry problem. So if you take a look at this drawing here on the left-hand side, there are multiple self-interested parties here which aren't sharing information. So, yes? All right. I'm not sure why. Can you see a slide 2, problem setting and objectives, that I'm on at the moment? So you can't. That's weird. Give me a second. I'll try again. All right, so I'm starting the slideshow on slide 2. Can you see it? Right. No, I don't. Let me try again. How about now? Okay. I can just go through. Yeah. Okay. Okay. Let's do that. All right. No problem at all. Thanks for letting me know. So co-located suppliers, they don't know that they are sending items to similar locations at similar times. And for retailers, orchestrating the co-loading, that would involve transactional costs. And the benefits of orchestration, the benefits of orchestration wouldn't really outweigh the costs of orchestration, so they have no incentives for orchestrating co-loading. And for logistic providers to be a co-loading operator, then suppliers would actually need to use the same logistic providers, which then would create a lockdown effect, which is not suitable for sporadic journeys. And for a third-party mediator to orchestrate, then multiple suppliers would need to sign up and pay for it, and they won't see the benefits from it unless all the other suppliers sign up. So it is a tricky problem. And the core idea of this feasibility study is to try and automate the finding of co-loading opportunities through what we call an agent-based system, so that the orchestration costs are avoided. So software agents are goal-seeking entities, and the field of computer science conceptualizes AI itself with software agents, intelligent agents, which are computational programs that mimic and then act on behalf of a human user. They sense and perceive their environment and take actions to maximize the probability of achieving their goals using various tools, such as the ability to learn from data, communicate and negotiate with other software agents, and optimize their behavior to reach rewards. So multi-agent systems are inherently suitable to logistics problems, because here each party will behave independently and seek their own goals, which is why we chose it for automating this problem space. So in our case, AgentChat will involve understanding what agent architectures can be built, how can agents learn to cooperate with one another, and also finding out what real-life considerations need to be taken into account so that they can be modeled within this problem. So we identified key agents in our problem setting as orchestrators, shippers, customers, customer and shipper sites, carriers, and trucks. So there are many different agent types, and the scope of the roles of each of these agents will vary dependent on the agent architecture that we develop. So initially, we developed a system architecture based on these different types, and identified messages that need to be sent containing all necessary information, such as purchase orders, advanced shipment notices, and so on. And the goal is to create a scalable architecture so that these messages are distributed among agents as much as possible, so no one agent becomes a bottleneck in the system. And initially, we followed a centralized approach where we wanted to understand whether agents can learn to cooperate through a common reward function. So they have a common goal here. And in that setting, carriers have multiple delivery requests, and they are sharing those requests to minimize a total distance traveled, giving away deliveries that do not necessarily benefit them. So this has been possible, I'm pleased to report, where we observed an optimality gap of only 1% compared to mathematical optimization, which aren't very scalable. So a more realistic setting, though, would be, we think, self-interested agents, where agents don't share reward functions, but only care about their own rewards. And that would then result in them trading off the gains that they obtain from delivering an order, which itself is a function of distance traveled versus the price paid by their customer, versus the gains that they obtain from outsourcing that particular order to another carrier. So sharing with another carrier the load, but also paying to the other carrier as a result. So in other words, the agent here will choose to deliver to a faraway location if the other carrier is not offering enough of a bid for that particular order. So what this means is that in the AI world, what this becomes is a bargaining problem. And given that we have multiple players in this in the bargaining problem, we have an n-player bargaining problem. So agents need to iteratively bid for orders and converge on a solution. And we are currently working on modeling this problem, and then we'll compare that with the common reward function that we already have benchmarked on. But this problem hasn't been well handled in literature so far. So this is kind of a longer stretch goal. And we selected carrier agents to be exchangers of information at this particular instance because they have an overview of the marketplace. This subsequently means that carrier agents take on the role of orchestration and value sharing. But as we move towards more decentralized marketplaces and self-interest agents, it might very well be that shippers and customers take part in the decision to co-ship. And in that scenario, the role of a platform would be to facilitate data exchange rather than matchmaking. And individual organizations would then need to develop capability to plug in to the decentralized marketplace to take automatic decisions. So the problem becomes a little bit more complex from an infrastructure perspective, but then everybody gains. Speaking of complexity, so the actual problem size and context is quite high. And the complexity of the optimization problem is quite tricky as well. So firstly, given a finite truck capacity, and I'm sad that I can't show the animation here. I wonder if you can see it now. So the given a finite truck capacity, we have a set of loading constraints which involve the order in which items can be loaded onto the truck. So we maximize packing, but also allow ease of unloading. So that's a sub-problem that we are considering in a three-dimensional context. So here you can hopefully see a small animation prepared by Stefan, who's been working on converting the 2D packing into a 3D packing problem as the vehicle travels and is shared along the route. Further, there are many other constraints we haven't considered yet. These include axle weights, goods compatibility, and the pickup timing and duration that need to be included in the travel time estimation. So to give you an idea about the vastness of this problem, here are a number of UK-based statistics. There are about 10,000 carriers in the UK and 1,000 shippers, excluding home parcel deliveries, and 50,000 locations to be delivered. So, of course, from a platform perspective, our problem size would constitute a much smaller number of carriers, but nevertheless, scale becomes problematic. And this is my final slide. So, in the scalability strand of our work, hopefully you can see the slide. So in the scalability strand of our work, we've been investigating software design and how messages can be minimized whilst information requirements are fulfilled. Our initial demonstrator included about 100 locations and 8 vehicles, which was solved under about 60 seconds. So it's worth mentioning that because of the complexity of the problem, we haven't had time to integrate these 3 sub-problems I talked about, which is the bargaining game, the capacitated collaborative vehicle routing, and the scalable architecture. But as we are making headway in these sub-problems, we will increasingly be looking to integrate and maybe trading off optimality with scalability. An interesting venue to explore in the future will include the role of platform providers here. So we could create a decentralized platform where agents search for service provision and contact one another. So agents are only charged to exist on the platform. Or we could aim for a platform offering where matchmaking is done by an intermediary and agents are then charged for this service, but then they lose their agency basically as the matchmaking is only left to the platform owner. So, so these are a number of our interesting research venues that we are looking to explore, and please do get in touch if you're interested. So may I just wanted to take the opportunity to thank our team members who will join me now on stage, and thank you for listening.